hoping this works. Okay. We're getting to the end here. It's going to be a few more lectures, maybe 5 or 6. And some review sessions too. So we'll start multiprocessors today, but before that, we'll wrap up prefetching, and then we'll jump into it. I don't have announcements, but you know that you have an exam coming up next week, right? Next Wednesday. We discussed that in the last lecture. So I'm hoping everybody will ace it.
And the homework is also due that day?
Homework is not due during the exam day. It's actually due much later. But last day of classes. But I definitely recommend that you do the homework for the exam. Yes?
Just for both, like, Chada, are we allowed to use late days on the last lab?
So we're going to give you the policy later on.
Okay.
Can you give us the policy like
Before lab 6 is due.
Friday?
So
we can budget late days.
I see. So lab 7 will be special. We're going to allow other people, everyone to have more time,
Okay.
if that makes sense. So if you're going to use late days for lab 6,
Use late days.
use late days for lab 6. But the exam is soon after lab 6, so I'd recommend that you don't go late with lab 6. It's an easy lab, so it should be.
Unless you have 7 late days.
Unless you have that's right. Yeah, unless you have 7 late days, then you can do it after the exam. That's right. Yes. Absolutely. Who has 7 late days? Well, that's great. Okay. So yeah, that's a good question actually. For lab 7, we'll do something special, and everybody will get a chance, even if you don't have late days. Okay? Happy? And I would like you to do lab 7 because lab 7 is so important. Well, it's related to what we were going to talk about today. It's implementing coherence in C-level simulation, and coherence is so important. So you're lucky to get to implement coherence at an undergraduate level class like this. Because you're gonna be dealing with coherence in any place where you have caching that is employed, not only in multiprocessors but also in distributed systems. If you cache in a distributed system, you're going to run into coherence issues, right? I always run into coherence issues with Google, for example, with my Gmail. If I have Gmail open in different places, you see that they're not consistent, right? They're not coherent with each other. I also have consistency issues with Gmail too, but we'll get back to that when we talk about consistency. Okay, and Gmail that's a big distributed system, right? But that's no different from the small scale multiprocessor that we have today, except for the scale itself. Okay, so some buzzwords on prefetching. I'm going to wrap up prefetching. These were some of the things we covered, and this is with a stream of consciousness. I wrote this down when I was preparing for this lecture. But these are the key things to know. Like, there were 4 key questions: what to prefetch, when to prefetch, where to prefetch, and how to prefetch. And how could be in 3 higher level methods. You can have a hardware prefetcher, software prefetcher, or you can have an execution-based prefetcher, which we did not talk about except for the high level idea, which we'll talk about today. These were some of the metrics that were important: accuracy, coverage, timeliness, bandwidth consumption, cache pollution due to prefetching. You talked about the aggressiveness of the prefetcher, and in particular for hardware prefetchers, you have prefetch degree and prefetch distance. Hopefully these are coming alive in your head now. And we talked about prefetcher throttling, such that you're not too aggressive. You limit your aggressiveness such that you improve performance. And we have talked about, we've ended the last lecture before the Spring Carnival talking about prefetching for arbitrary access patterns or arbitrary address patterns. And we talked about the idea of Markov prefetcher, for example, which can prefetch for addresses that have no relationship to each other, except you need to see these addresses in sequence previously. We talked about content-directed prefetching, which is like a cool idea in my mind. Basically, you examine a cache line that you bring into the cache, and you try to find the pointers in that cache line with some heuristic. Hopefully you remember the heuristic. Once you find those pointers, you prefetch those pointers. This way you don't even need to see a pointer before you actually can prefetch for that linked data structure that hopefully the pointer points to. So this is actually a very interesting and rich area of research. And modern prefetchers, by the way, modern processors employ prefetchers very aggressively. And this is one of the places where microprocessor performance improves significantly because memory latencies are so high today. Okay, now let's focus on execution-based prefetching. We talked a lot about hardware and software, so I'm going to finish with execution-based prefetching. The key idea here, I've given you the idea before, is to pre-execute a piece of the program solely for prefetching data. And this piece of the program can be a part of the program you pre-execute early, or a pruned piece of the program that you actually generate, that somebody generates, either the compiler or the hardware or the programmer, such that that piece can be executed early, and the piece can be computing the addresses that are later going to cause cache misses. Basically, you only need to distill pieces or instructions that lead to cache misses. So this distilled piece of the program can be called a speculative thread, right? This is the pre-executed program piece. It can be considered a thread. And we can construct this thread and execute it in parallel with the original program, such that while the original program is doing a bunch of things, this pre-execution thread is executing somewhere. It could be on a different core, for example, or it could be in a different context, and prefetching data for the original program. And by the time the original program gets to access the address that the prefetching thread is actually prefetching, hopefully that thread has already brought the address into the cache, and the main program doesn't need to stall. That's the idea, basically. It's actually a beautiful idea. This is also called a helper thread. Helper thread is more general. This is a prefetching thread, speculative prefetching thread. But you can actually use this helper thread for other performance degrading instructions, such as branch instructions as well. And I'll give you an example of that. So one key consideration in this kind of prefetching is the speculative prefetching thread can be executed in many different places. It could be executed on a separate processor or core. It could be on a separate hardware thread context. For example, in fine-grained multi-threading, one of the thread contexts can be dedicated to the main program, and the other thread context may be doing helper thread-based prefetching. Or on the same thread context in idle cycles during cache misses, for example. I already mentioned that run-ahead execution is a speculative execution-based prefetcher, right? We'll get back to that at the end of this part of the lecture. But basically, whenever you get a stall in the main program, you can bring in this prefetching thread to do useful work while the main program is being stalled. The hope is that in the future, the main program will not stall because this prefetching thread does some good prefetching. Make sense? So there's actually a very large design space, and we'll see that there's more. So one key question is, how do you actually construct the speculative prefetching thread, right? You could do this in many ways. You could use software to do this. Compilers can do this, or the programmer can do this. They can identify instructions that lead to these cache misses and prune a small thread and insert a spawn instruction somewhere in the main program. And when the main program gets to that point, it spawns this speculative thread that will do prefetching. And we'll see an example of that. The hardware can do this, although it's more difficult than hardware, you can imagine, right? You need hardware to actually construct a thread, to figure out which instructions are leading to cache misses, and to insert a spawn instruction such that this thread can be launched to do prefetching. And people have proposed both mechanisms, but software currently is more viable. And I'll give you some examples from recent research. Or you can use the original program. You don't need to construct a thread this way, which is beautiful, which is simple, but somehow execute it faster without stalling and without having correctness constraints. Run-ahead execution does this, right? It basically uses the main program, original program, to do pre-execution while the main program is stalled. And run-ahead execution ensures that this pre-executed piece of the program doesn't stall that much, using the invalid bits and dropping instructions that lead to cache misses, right? That cause cache misses. So the speculative thread, one key thing that's important in this is it needs to discover misses before the main program, right? If you execute the speculative thread and it discovers the misses much later than the main program actually stalls for the miss before the speculative thread gets to it, there's no point in doing this. You'd be wasting energy. So in order to do this, you need to avoid waiting or stalling and or compute less in this thread, right? How do you actually get ahead with this thread? Basically, you construct a lean thread that can do this prefetching much faster than the main program can do. And you can actually use other techniques. We're not going to go into this in detail in this course, but when you take 742, if you take 742, we can go into a lot more detail as to how you can make this prefetching thread a lot more effective. For example, because this is purely speculative, if the value of a register is not available, the speculative thread can say, oh, I'm going to predict this value and I'm never going to verify it, right? Assuming that value prediction is correct, hopefully you'll get good results in prefetching, right? And of course, performing only address generation computation enables this thread to get ahead. Performing branch prediction and value prediction to predict some of the unknown values. Because when you construct a speculative thread, you're actually cutting the program at some point, right? And the values may not be available yet, right? Actual values may be produced by somewhere in the program, and that part of the program may not be executed yet. So how do you get ahead? Well, you somehow do a speculation, which is value prediction and branch prediction. We're not going to get into this, but you can imagine some of the registers may be predictable, and the speculative thread gets ahead of that. Gets ahead by doing that prediction. And one key important thing is, just like run-ahead execution, this execution-based prefetchers employ threads that are purely speculative, so that there is no need for recovery of the main program if the speculative thread is incorrect. Again, this is prefetching, right? If the speculative thread does something that's incorrect, let's say generates an exception, well, you can even ignore it, right? You don't need to do anything because it's purely speculative. So this is one nice example. I believe it's from one of these, maybe from this paper, that shows the benefits of thread-based pre-execution in general. Let's take a look at this load over here. And this is the main program that's executing. Let's assume that we have a fork point that launches a speculative thread to do prefetching for this particular load that we've somehow determined is likely to miss in the cache. So somebody constructed the speculative thread, and somebody inserted this fork point for that speculative thread. Fork point is the same as spawn point. When the main program reaches this fork point, a thread is forked to do prefetching for this load, and it executes some instructions, a prune part of the program. It doesn't execute all of the instructions over here. It executes a small number of instructions that hopefully generates the address for this load. It does execute that load with its address, and that hopefully leads to a cache miss. And while that thread is executing and while that cache miss is being serviced, the main program is actually executing all of the instructions that it needs to execute. And that execution of those instructions are overlapped with the speculative thread and the cache miss. And hopefully by the time the main program executes this load instruction, it hits in the cache because the miss was serviced by the speculative thread. And as a result, you get a speed up. It's beautiful if you can do this. Of course, the cost is this needs to be executed somewhere. Right? You could do this for other instructions as well, and some of these papers actually discussed how to do this for branch instructions, for example. For example, if this is a difficult to predict branch, you can construct a speculative thread that computes the outcome, and that is launched much before the branch needs to be executed. And this thread actually computes the outcome of the branch with some speculation by executing instructions that only lead to the computation of the outcome for that branch. And by the time this branch is fetched, you actually have a prediction for that branch based on that pre-computation. Of course, there are a lot of issues. Where do you store that prediction, for example? How does the branch figure out that there's a prediction computed by this thread? But those all can be handled, right? You're now architects. You can think like an architect. For example, in the BTB, you can set a bit saying that, oh, I have a better prediction for this branch than the branch predictor because the speculative thread actually computed the result. And when this branch is fetched, it gets a hit in that BTB entry, and you check the BTB entry. Okay? So you could imagine doing this for other instructions as well. It's a pretty powerful concept. But there are a lot of issues. Like, there are a lot of questions that need to be answered. First, where do you execute this pre-computation thread? I call this the pre-computation thread, speculative thread, pre-execution thread. They're all the same thing. I'm not going to go into the detail, but I'd suggest you think about like what are the implications of this, because there are a lot of implications as to where you, based on where you execute this thread. You can execute in a separate core, right? You can have two different cores, and main program can be executed here. Speculative thread can be executed here. If you do this, let's say the cores have a cache hierarchy like this. They have private L2 caches. Obviously, they have private L1 caches, and maybe a shared L3 cache, and a shared memory system after that. In this case, the speculative thread doesn't contend for resources with the main program in the processor or in the private L2 cache or in the L1 cache, right? Which is nice because it doesn't slow down the main program. But the downside is now speculative thread cannot prefetch into the L2 of the main program unless there are special instructions that say push this value here. The speculative thread prefetches into the L3 cache, right? The shared cache. So there's an upside and downside. You could execute the pre-computation thread in a separate thread context. Think fine-grained multi-threading, right? Or maybe simultaneous multi-threading. We'll get to that also. In this case, now you have more resources. The main program and the speculative thread are executing on the same core. And the speculative threads, except on different thread contexts, and they're sharing the L1 cache, they're sharing the L2 cache, they're sharing everything else. And they're contending with each other much more. So main program may actually be slowed down because the speculative thread needs resources to execute. And speculative thread may bring in some data into the caches that may not be used later, even though it's doing prefetching for some other load. Okay? Or you could execute the pre-computation thread in the same core and the same context. This is like run-ahead execution again. When the main thread is stalled, you bring in this thread. Again, there's contention. The pre-computation thread contends with the main thread in this case, just like run-ahead execution contends with the main thread, right? You could think of run-ahead mode contending with the normal mode. If run-ahead execution does something bad, meaning it fetches data that's not going to be used later, you may be polluting the caches. Right? But hopefully the contention is not as bad as in multi-threading because you're not concurrently executing the main program and the speculative thread. Okay? So this hopefully gives you a brief idea of like what are the trade-offs. The second question is when to spawn the pre-computation thread. This is very similar to how early actually you should prefetch, right? It's the same idea. Ideally, you would like to insert these spawn or fork instructions well before the problem load. Problem load meaning cache missing load. But how far ahead may be difficult to determine. This is like software prefetching, right? As we've discussed. If you do too early, the prefetch that is generated may not be needed, and you may actually never get to execute that load in the main program. If you do too late, prefetch may not be timely, right? It's the same problem with software prefetching, except now it's not for a prefetch instruction, but for the spawning of a pre-computation thread. Or you could spawn it when the main thread is stalled. This is the same choice as this one. And there's another question. Now, you may want to actually terminate the pre-computation thread sometimes. And the question is, when do you want to do that? And I'll show you an example where the programmer or the compiler can insert cancel instructions. Basically, you cancel the execution of the pre-computation thread. Or maybe when the pre-computation thread is going too slow, when the main program catches up with the pre-computation thread, it can execute this cancel instruction. Or you can use techniques like throttling that we've discussed. You can adapt some of the techniques that we've discussed for hardware prefetchers for this pre-execution thread. If the pre-execution thread is not effectively prefetching for the main program, and you can collect this data over time, and you can feed that back into the main program. And when the main program gets to a spawn instruction, checks a buffer that says, oh, in the past, pre-execution threads have been this much useful, let's say. And if that usefulness level is not acceptable, then those spawn instructions may be ignored, right? So there are a lot of design choices here. Obviously, I'm not covering the entire design space. So I'll give you one example of how this is done using software with some hardware cooperation. This is the paper. I didn't assign it, but if you take 742, you'll probably read a paper like this. But basically, this discusses how to construct pre-execution threads and how to execute them in a simultaneous multi-threading processor. Basically, there are many issues that are discussed. And these are some examples where constructing a pre-execution thread is beneficial. For example, if you have a program that does this, it basically has a bunch of lists, and it goes through these lists and traverses each of them one by one. While the main program is working on this list, the pre-execution thread may be prefetching for this list, right? And maybe another pre-execution thread may be prefetching for this list. That's the idea. If these list traverses are independent of each other, you can actually overlap the prefetching of this list while the main program is working on this list. Why could this happen? Well, this is an example of a hash table, right? If you think of this as a hash table, each linked list is part of the bucket of the hash table. And when you're actually searching for a key in that bucket, maybe you will later search for some other keys in some other buckets. And a pre-computation thread can prefetch those buckets, those linked list entries in those buckets. There are a bunch of other things. Another example, you can read the paper for these other ones, but another example is when the main program is working on a function, let's say foo, the pre-execution thread can be launched to prefetch a later function that you expect to be called by the program. Make sense? If the program is going to do these functions, foo, bar, buzz, puz, I don't know how you read that, but basically you could have pre-computation threads that are just doing these functions solely for prefetching, and control flow paths as well. So this is one example that shows this one actually. Again, I'm not going to go into detail, but this is just to show that this can be implemented. Basically, this is an example from MCF. It's a vehicle scheduling program that was actually one of the most memory-intensive programs in the spec workload suite that processors were evaluated with for a while. And what it does is it basically has this while loop that traverses a linked list, and it also has this for loop that initiates a bunch of these different independent while loops, independent list traverses. So while the main program is working on this list, you can actually generate a pre-execution thread that does the next iteration of this for loop. And that's what this text that I copied from that paper actually explains it pretty crisply here. And I'd like, you can read it from the lecture slides. You don't need to read the paper. It's pretty self-contained. But basically, in order to be able to prefetch for the next iteration of the for loop, which is the next list that's going to be traversed by this program, the programmer or the compiler can insert this pre-execute start instruction before this while loop starts. And this pre-execute start tells that the pre-execution should start at the end for at this point, which basically iterates the loop iteration count. So when the thread starts, when the speculative thread starts, it increases the iteration count, induction variable, and something else that's needed for loop iteration. And then it goes to the next iteration. That's the speculative thread. Which means that the speculative thread keeps executing the next iteration while the main program is actually executing the previous iteration. Right? And when the speculative thread reaches pre-execute stop instruction, it terminates the pre-execution, such that it only prefetches the next iteration. Make sense? You don't need to have pre-execute stop here. You could actually keep going, but that makes it the speculative thread to go further ahead. Okay? So you can read this for more detail, but you get the idea, right? While the program is doing one iteration of the loop, the speculative thread is doing the next iteration of the loop. So what kind of ISA support do you need to enable this? Obviously, you need to be able to start a speculative thread with some start PC, and maybe you can supply maximum number of instructions that the thread should execute, and after that it should stop. This is to control the speculation, perhaps, right? And this is one example, so take this with a grain of salt. You could imagine other definitions of this. You will need to be able to stop the thread because you don't want it to go forever, right? And when the thread executes its instruction, it will terminate itself. And you can have a pre-execute cancel instruction, which I don't believe is shown here, but it's in some other example in that same paper. In this case, the main program can actually terminate the pre-execution thread with some thread ID, because the main program may already reach that point where the thread is not useful, because it may have already reached this point where the load is being executed, right? Almost executed. Okay, so these are some results based on this paper again. It shows that you can actually get, on a simultaneous multi-threading processor with two hardware thread contexts, you can actually get significant performance improvements. And I'm not going to go into detail here. You can see that for this workload, the execution time reduces by 24%, just by using this speculative thread that's constructed by software. And some other workload, the minimum spanning tree program, I'll give you examples of this actually when we talk about content-directed prefetching. There are significant pointer-based traversals, tree traversals. In this program, it gains 36% performance improvement with just one speculative thread. And you also see that the world is not always rosy, right? You can see that this compression program loses performance. Its execution time increases because you're doing this, you're using the speculative thread for prefetching. And I believe one of the reasons is because the speculative thread is actually contending with the main thread and slowing down the main thread's execution. And it's not being beneficial enough to overcome the effect of that overhead. So the performance of the entire program reduces when you execute the speculative thread. So you've got to be careful when you actually construct these threads. Okay? So you can actually generalize this idea. I've already shown you that picture. But this can be applied to many different instructions, not only cache misses. And these are, again, 2 papers that describe it. Again, I'm going to go through this relatively quickly. But this is another program, virtual place and route. Basically, it does place and route for a circuit. And it's actually a tough program because it's both memory intensive and branch intensive. So this particular statement leads to cache misses and also branch mispredictions. So in order to speed up the execution of this statement, you can have a speculative thread that is launched before this add to heap function is called that pre-computes the outcome of this branch, and that also pre-computes the address of this load instruction. And we'd like to construct 2 speculative threads for this purpose, and this paper describes how to do that. So first of all, where should the spawn point be? This is the function that's called. If the spawn point is too close to the problem instructions, well, it's too late to this. So you would like to raise the spawn point to somewhere before this function is called. And that's what they do over here. This is the fork point or spawn point of the thread. It's raised way before this add to heap function is called. And again, don't be scared with this, but this is the assembly code somewhere around here, I believe, including the add to heap function. But this is the entire main program that is executed, including all of this, I believe. This is just to show that the speculative thread that's used to compute this branch outcome and this load address doesn't need to be as large as the main program, because not all instructions in the main program lead to the computation of that branch outcome and the cache block address of that load. So this is the prune thread, if you will. This is a speculative thread that's formed by hand in this paper, and it only needs, I don't know how many instructions, 1, 2, 3, 4, 5, 6, 7, 8 instructions, right? Whereas the main program needs, I believe, more than 20 instructions over here. So this is how the speculative thread can get ahead of the main program. First, you raise the fork point to a place that's much earlier than the problem instruction. Second, the speculative thread itself is much smaller because it doesn't need to do all the computations that the main program needs to do. Okay? It's beautiful, right? Well, I guess I'm not going to go through run-ahead execution again, but I'll just say that run-ahead execution actually is the same thing as an execution-based prefetcher, right? You start pre-execution when the main thread actually stalls, or when the main thread actually gets a long latency cache miss. And run-ahead mode can be considered a pre-execution thread because you're really saving the context of the main thread to the checkpoint. And during the speculative thread execution, the main thread is not executing, but the speculative thread is actually prefetching for the main thread such that the main thread doesn't need to stall when it encounters this load to instruction later on. Okay? Okay, so that's the analogy, basically. Run-ahead execution is an execution-based prefetcher too. Okay, I think that's all I have for execution-based prefetching. Any questions? It's all clear? Now you can all write these execution-based prefetchers. Lab 8. So you'd like to stay for the summer, huh? Maybe in a later lab. In 742, definitely. Okay. Let's jump into multiprocessing. It's a bit early, so I don't want to take a break right now. So we're going to talk about multiprocessing. And all of the processors you have today are pretty much multiprocessors. I don't know if anybody has any device with a single core processor, or any high-performance device at least. It's hard to find single core processors today. And these are some readings that I'd like you to do. These are the required readings. I hope you've already done the Amdahl's law reading, Amdahl's seminal paper on Amdahl's law. Who's already done it? No class requires you to do it? It should be required in 213, I think. This is such a fundamental law, right? And it's only a 2-page paper actually that describes the law that you've gotten to know and love, right? And cannot avoid, unfortunately. And the second one is, again, only a 2-page paper that talks about sequential consistency. We're not going to cover it today, but it's a seminal paper by Leslie Lamport, How to Make a Multiprocessor Computer That Correctly Executes Multiprocess Programs. It talks about sequential consistency, memory ordering, and we'll talk about that in the next lecture. So definitely do these readings. We're going to talk about Amdahl's law again today. And these are some recommended readings. When we talk about cache coherence, again, this is going to be next lecture, or the next lecture. These are some supplemental readings. I say these are required. They're not really required, but this will definitely enhance your understanding. So consider these required. And we're going to talk about the MESI protocol, which is variants of which are used in pretty much all multiprocessors today, at least shared memory multiprocessors today. MESI, or the Illinois protocol. And this is the paper that introduced that protocol. Okay. Remember Flint's taxonomy of computers. I had put this up when I introduced SIMD machines. You've covered a lot of machines that fall into this taxonomy. SIMD is single instruction, multiple data. Right? We've covered vector processors, array processors, GPUs. SISD is single instruction, single core, single threaded processors. MISD, multiple instructions operate on single data elements. We've covered the closest form, systolic array processors. Now we're going to focus on MIMD. We haven't, although we've kind of talked about MIMD in many places in the course. For example, in memory scheduling, when you have multiple cores sharing the memory system, we haven't really covered it in depth. So we're going to talk about how multiple instructions operate on multiple data elements using multiple instruction streams. But before we go into that, so all of these, or many of these, try to exploit parallelism in some way. And usually when you think about a multiprocessor, you consider that as a parallel computer, although a SIMD processor is a parallel computer too, or out-of-order execution processor is a parallel computer too. But when we talk about parallel computing, it's usually multiprocessing or multi-threading. And parallelism means doing multiple things at a time. Things could be instructions, operations, and tasks. The main goal has been for a long time, from the very beginning, is to improve performance. Somehow reduce the execution time of a single task by dividing into smaller tasks, or improve task throughput if you have many tasks. This improves performance by having multiple processors execute those different tasks. We'll get back to this, but execution time of a program is governed by Amdahl's law. There are actually other goals in building parallel computers or doing multiple things at a time. Anybody can guess what those other goals could be? There are 3 of them, but there could be more. What else are you trying to optimize for other than performance? Power, yes. I think that's the first one, right? You can reduce power consumption, right? Why? Because instead of designing one single unit that accomplishes the amount of work that you want to accomplish, you are designing more units that accomplishes only a small part of the work that you're trying to accomplish. Which means that those smaller units can be much more power efficient. And here, in this slide, I give you an example of, in this case, I take only frequency as an example, but let's assume n is 1. Instead of designing one unit at frequency f, assume that frequency is the only thing that matters for performance. Instead of designing one unit at frequency f, if you can completely parallelize your program, you can design 4 units or 4 processors, each of which is operating at frequency f over 4, and each of which is doing 1/4 of the work. Right. This way, these units will finish the program at the same time as this unit, hopefully, assuming frequency is the only thing that matters for performance, except this will be much more power efficient, right? Why? Remember the power equation. Dynamic power is equal to CV square F, right? Where this is the capacitance. Assume capacitance remains the same, although it doesn't necessarily remain the same because these are probably smaller processors, so maybe you can reduce the capacitance of this too. The frequency of execution, here it's F, here it's F over 4. So the power of this is proportional to some C V square F, whereas the power of this is proportional to C V square F over 4. Right. Now it's not So basically you get a linear savings in power consumption. It's actually much better than that, because now you need to support a smaller frequency, a lower frequency. And a lower frequency doesn't require a high voltage. Usually, to support high frequency, you need to increase the voltage of the transistors. Now you can actually reduce the voltage to V over 4. So what you get over here is a quadratic effect, quadratic reduction, or cubic reduction on power consumption. Does that make sense? So, yes?
Aren't there like 4 processors though, so it's like 4 times that power?
That's a good point. Okay.
So it would be like that, so that over 4 would like be.
That's right, yes. Now you get a quadratic reduction, right?
Yeah, the voltage would be.
Exactly, yes. So that's an excellent point. Basically, you still get a square root of a quadratic reduction instead of the cubic reduction. Okay. For one processor, you get the cubic reduction. So this is a lot more power efficient, right? If you can do this. I say if you can do this because there are a lot of assumptions that we made over here, right? One is the program itself, the work that you're doing is completely parallelizable, right? Such that this processor, when it executes it, it'll end at time t, and all of these 4 processors will end at time t at the same time. If that's not the case, well, then you have a problem, right? When these processors execute the program, they'll end at a later time. So they'll be operating for this amount of time, which is longer than the single processor, and they'll be consuming power during this amount of time, right? So you can actually lose on energy efficiency and power consumption if that's the case. But this was one of the motivations for actually designing multi-core systems, such that you can reduce the power consumption by building these simpler processors. It works only if the work is completely parallelizable. What else? What could be other motivations? Yes?
Like a better problem fit.
Mhm.
So some problems are inherently parallel.
Mhm.
You have a parallel system, and there's a better fit between the problem and the implementation.
So that's true, but that will improve performance or power consumption. That's true. It could be your problem may be fitting a parallel computer better, but eventually your goal is to do something, right? Improve performance of the problem or reduce the power consumption. Yes?
Can you increase the density because you won't have to have those ridiculously space inefficient optimizations that you use to try and increase performance?
That's right. Well, I will rephrase it in some other way. You can improve cost efficiency and scalability and reduce complexity, right? Because it's probably very hard to design this single unit that can achieve high performance, whereas it's much easier to design these smaller units because they don't need to be as high performance, right? In fact, frequency is only part of the problem. You can make these lower IPC as well, right? So you don't need out-of-order execution, for example. Instead of designing a huge out-of-order execution engine, you design a bunch of wimpy in-order engines at lower frequency, right? And this is much, much easier to design than this beast, right? In fact, I would say this is the main motivation that industry had for multi-core, because it was very, very difficult to increase performance by building bigger and bigger, more and more complex out-of-order execution engines that not only led to higher power consumption, but also increased the design verification and validation costs significantly, because verifying a complex design is much more difficult than verifying a simple in-order wimpy pipeline, right? I know you're doing the wimpy pipelines in this class, but imagine doing a much stronger, much bigger out-of-order execution pipeline, right? That's a lot more costly. And the design times, the times to market of these out-of-order execution processors we're at the point of being dominated by the verification and validation costs, right? Actually, approximately 40% of the time to market, design time, starting from the design from scratch to when you market the processor, approximately 40% of that time has been spent on verification and validation of the design instead of the design itself, right? And by designing these simpler processors, you can improve cost efficiency, scalability, and reduce complexity. And you can actually put more processors, as you've said, right? Because there's a lot of overhead area, control logic here, that's not needed here. What else? There's actually one more reason. This is usually the tough one. That's why it's ordered this way. That's actually another old reason why people have built parallel computers or multiple units. Anybody? No? Yes? You're going to venture, I guess?
I was gonna say that it can help with prefetching in
Okay.
terms of like reducing the
Mhm.
complexity, because you could just throw
Mhm.
another core at it and have it do the run ahead execution or whatever.
That's true, but those lead to these, right? You
Yeah.
can either improve power consumption or performance. Probably more performance. No? Well, if you have one unit, what happens if that fails? Well, you're done, right? You cannot do anything. But if you have two units, if one fails, you can use the other one, right? And that's a fundamental reason why you want to have parallelism or multiple units. You can improve dependability, basically. You can have a cold spare, as I described it, meaning if you have one unit, the other thing comes up. Or you could actually operate these units together in parallel and pick the answer that's the most common across all of those units. Right. You can have 3 processors, and maybe some of them are faulty, but as long as 2 of them agree on an answer, you pick that as the answer. Right. That's the idea of redundant execution in space. You're executing the same program redundantly on 3 processors and picking the answer that's the most common across all of those processors. This is called triple modular redundancy. If you have 2 processors, you can execute the same program on the 2 processors, and if they don't agree, then you know that something may be wrong, right? At least you can detect a fault with 2 processors, dual modular redundancy. And you can generalize this idea. You can have 1,000 processors all executing the same program, and if you really care about the answer, then you'll hopefully get the right answer. Okay? That's the third fundamental reason. And if you have a 4th one, let me know. Okay, there are actually different types of parallelism. We're going to cover more task-level parallelism with multiprocessors, but let's cover instruction-level parallelism. Instruction-level parallelism, different instructions within a stream can be executed in parallel, right? And actually, all of these principles apply to all different types of parallelism, right? For example, you can have, even in an out-of-order, single-threaded processor, when you design adders that are really fast, you may get these faults, right? Especially when the circuit technology scales to smaller feature sizes. Today we're at almost 11 nanometers. Right? At 11 nanometers, you get these effects where your circuits become faulty. So you may not want to have a single adder that does the add operation, but you may want to have three adders that do the same add operation redundantly and pick the most common answer within the out-of-order execution process. Right? So let's get back to this. Different instructions within a stream can be executed in parallel to exploit instruction-level parallelism, and we've seen a lot of techniques for this, so you know all of these by heart. Data-level parallelism, we've also seen that. Different pieces of data can be operated on in parallel. SIMD processors, systolic arrays, they're all data parallel processors. And task-level parallelism, this is something we're going to talk about in more detail. In this case, different tasks or threads can be executed in parallel. Multi-threaded processors, multiprocessing, and multi-core, of which is a special example of multiprocessing. So how do you actually create these tasks is the other question. You can partition a single problem into multiple related tasks, just like we've discussed over here before. Remember, I've given you the example of counting the number of letters in an entire book, right? If the book has n pages, and if you have 4 processors, you can partition the n pages such that you assign n over 4 pages to each processor, or each thread, or each tasks. And each task produces a histogram of the letters for the n over 4 pages that is assigned. Right? That's a nice program, nice problem that's nicely parallelizable. Right? Not all problems are like that. And those tasks are related now because eventually they need to cooperate somehow to gather the final histogram, right? Because you want the histogram of the characters for the entire book, not only for 1/4 of the book. So you could do this explicitly. This is called parallel programming, and there are many ways of doing that. And this is easy when the tasks are natural in the problem. And this was an example. The example I gave, I would consider that tasks are kind of natural, right? You're counting. It could be words, it could be letters. You're counting letters in an entire book, and clearly you can divide the book into a collection of pages. And there are other cases where tasks are natural in the problem. For example, you can have queries to a database, even though there's some shared data that needs to be synchronized when multiple queries access that shared data and one of them updates it. These queries can be mostly independent. This is more difficult when natural task boundaries are unclear. For example, parallelizing a compiler is usually a difficult task. You could do it, but some parts of the compiler are difficult to parallelize. We can talk about this for a long time, but I'm going to skip that. That's a difficult problem. How do you actually make parallel programming easier? The second way you can partition a single problem into multiple tasks or multiple threads is you can do this transparently, implicitly. And I'm not going to talk about this, but when you take 742, you'll see an idea called thread level speculation. In this case, you partition the program into multiple tasks, except the tasks are speculative. And they need to be verified to complete. And this could be done without the support from the programmer, without being programmer specifying the tasks. The hardware can do this implicitly. For example, one idea is if you have loop iterations that are mostly independent, and if you have 4 processors, the hardware can decide to spawn the next iteration on the next processor, and the iteration after that on the other processor, and the iteration after that on the other processor. The hardware may not know if these are completely parallelizable, but it may have the mechanisms to check if these loop iterations actually overlap with each other. They need data from each other. That's the idea. Basically, speculatively partition a single thread on multiple processors. It's more difficult to do, obviously. But now, the upside is the programmer doesn't need to do the parallel programming. The burden is not on the programmer, the burden is on the hardware. The second way of creating tasks is by running many independent tasks or processes together that have nothing to do with each other. This is easy when you have many processes, right? For example, batch simulations. You have different kind of simulations. You're using your simulators to simulate different workloads, for example. They have nothing to do with each other. You want to just get the execution time your future design would provide on each of these different workloads. Right? So you can send a batch simulation on a multi-core processor, and they can run independently. You can have tasks from different users. You can have workloads coming from different users to some cloud computing service, for example, and they could be executed in parallel on the cores. In this case, it's easy to generate the tasks, assuming you have this abundance of tasks. The downside of this kind of approach is this doesn't improve the performance of a single problem, single task that you're trying to solve, that you're trying to accomplish. But it does improve the throughput of all of the tasks that you're trying to accomplish. Okay? I think we still have some more time before we take a break. Let me introduce some of the fundamentals of multiprocessing. There are 2 types of multiprocessors, and they're employed heavily everywhere. One is loosely coupled, the other is tightly coupled. We're going to mainly focus on tightly coupled multiprocessors because this is actually an example of a network. Basically, the key distinction is there's no shared global memory address space in the loosely coupled multiprocessors, whereas tightly coupled multiprocessors share the global memory address space. One processor can access the memory of the other processor. Or actually, there's a global address space that each of the processors can reference. Right? That's the key difference. Well, the way I'd like to think about this is actually like this. This is loosely coupled processor, memory, processor, memory, processor, memory, processor, memory. And this processor cannot address any location in any other memory except for its own. So basically, if this processor generates an address, from 0 through n, it has to be serviced from this memory. If this processor generates an address 0 through n, it has to be serviced from this memory. ... Well, how do the processors communicate with each other? They send and receive messages to each other. They cannot address a location in memory to communicate with each other. This is loosely coupled. This is just like a computer network, right? Different computers communicate with each other by sending messages through some kind of protocol. Tightly coupled, tightly coupled is, I guess I'm going to revise this a little bit. You have 4 processors, and they share a single global memory address space. Let's say that goes from 0 through 4n minus 1. Right? Now this is, again, it could be physically shared, but it could be logically shared. Right? Basically, you can actually distribute this memory physically across the 4 processors, and they can all see this memory. How? Well, basically the memory that's physically close to this processor can contain the addresses that go from 0 through n minus 1. Memory that's physically close to this processor can contain the addresses that go from n to 2n minus 1. Similarly, 2n to 3n minus 1, and 3n to 4n minus 1. Right? And any processor can access any address going from 0 to 4n. Right? Whereas here, every processor has its own unique memory space. Okay? This way, this processor can reference a memory location over here. Right? Even though the memory is physically distributed, it's shared logically. So these 2 machines can look very, very similar. The key is whether the memory is logically shared or not. Okay, so this is the same as a multi-computer network, as I told you, whereas this is traditional multiprocessing, symmetric multiprocessing, and multi-core is an example of this, right? These are usually programmed via message passing. This is called the message passing programming model. Basically, you need to have explicit calls, send and receive for communication. And if you take 742, we'll go into more detail of that. Whereas this has a programming model that's very similar to uniprocessors, right? Basically, everything can be thought of in memory. You don't have another device that you need to communicate to, right? Except operations on shared data require synchronization, as we will discuss. Okay. Make sense? Simple. So we're going to cover a lot more of these tightly coupled multiprocessors because a lot of issues arise when you have a shared global memory address space. You can think of this as a distributed system also. Whenever you program a distributed system, you program using sends and receives, right? You actually marshal the data. You can, for example, execute a function on a different processor by marshaling the input data and gathering the returned output data results. There are many issues in this tightly coupled multiprocessors because they share the global memory address space. We're going to cover some of them, only some of them in this course. 742 will cover a lot more. One is, how do you do synchronization when you share memory? If one processor is accessing address X and the other processor is also addressing access X, how do you ensure that the state is consistent? So how do you ensure that at the high level? Locks and atomic operations are there for this purpose. Right? The other is, if you employ caching in this kind of system, how do you actually maintain the caches to be consistent? How do you keep them coherent? Because any processor can cache any part of the address space, and any processor can modify any part of the address space, except they need to know each other's modifications, right? Otherwise, you can run into issues with correctness. The third one is, this issue doesn't exist over here, right? The cache coherence issue doesn't exist over here because this processor has its own memory. It can cache it however it likes because the other processors cannot access that memory. It doesn't even exist for those other processors. Right? Ordering of memory operations, what should the programmer expect the hardware to provide? And we'll take a deep look at that in the next lecture. So hopefully you'll do the Leslie Lamport reading for this. And this actually turns out to be a difficult problem also. How should the order of memory operations look like to each processor such that you can write correct programs or correctly synchronized programs? There are a bunch of other issues we've seen. Resource sharing, contention, and partitioning. Basically, because you actually physically share some resources, how do you ensure you share those resources in a way that improves fairness and performance? This was a memory interference issue that we've seen in previous lectures, right? It's the same thing. Actually, these issues exist in the loosely coupled multiprocessors also. This is not related to logical sharing of memory, but more related to physical sharing of resources. As long as in any, remember when I talked about memory interference, in any system where you have physically shared resources, you'll run into resource sharing, contention, and partitioning issues. And that's true not only in the computing world, that's true everywhere in the world. The next one is communication. This is actually true for both of the kind of multiprocessors. How do these communicate with each other, right? What kind of communication infrastructure do you actually have such that these different processors communicate with each other, or these different memories, caches, communicate with each other? So we'll have a lecture on interconnection networks that provides a glimpse at this area. And load imbalance is another issue. Basically, this is related to how you partition your programs. When you have multiple processors and you actually partition your program across these processors, how do you ensure that load is balanced such that you don't have idleness in the processors, such that you make the best out of the processors? So we'll cover some of this in this course, but we're not going to go into all of them. Well, we actually covered enough about the memory interference resource sharing issue, but there's a lot more that we haven't covered. So a lot more of this will be focused on in 742. Just one aside before we take a break. But a lot of these issues exist in hardware-based multi-threading also. Basically, this is the MIMD model also. Multiple instructions, multiple data, right? All of these issues actually exist, assuming that the different threads share the memory space. You could actually have hardware-based multi-threading where the threads are loosely coupled, right? They don't actually share the memory space logically. They may share it physically, but they don't share it logically. They cannot communicate with each other. But that makes a little bit, not a whole lot of sense, right? Because you're actually sharing the memory physically. If you actually can address each other's memory locations, then you can communicate much faster. You don't need to send or receive messages within the same machine. Okay, so these are some examples of hardware-based multithreading. Again, 742 will cover a lot of this in detail. You've covered fine-grained multithreading quite a bit. You already know this. But there are other forms of multithreading. One is coarse-grained multithreading. The idea over here is you can, for example, do switch-on-event multithreading. You switch between threads in a coarse-grained manner. You still have multiple thread contexts supported by the hardware, but at any given time, only one thread context is running. When that thread context is stalled, you switch to another thread context. For example, there have been machines that were designed for example, one of Intel's Itanium, I believe Itanium 2, had switch-on-event multithreading. When one thread got a cache miss, the other context was enabled such that the processor would fetch from that context. It would switch to that thread very quickly. You could do this at every cache miss, right? Or you could switch based on some time quantum, right? You could say this thread is going to execute for 1,000 cycles, and then I'm going to execute this other thread. Right? This is more coarse-grained than fine-grained. Fine-grained multithreading, every cycle you switch to a different thread. Right? Simultaneous multithreading is the most complicated form. Basically, you can dispatch instructions from multiple threads at the same time, and you have the infrastructure to do that. This is good for improving execution utilization, and we'll cover this in 742 again. So maybe I'll give you this example, and then we'll take a break. That's a good idea, and then you can solve this. So here, I'm showing you a polynomial equation, and this is not perfect, but basically you have a4 x to the power of 4, a4 is a constant, plus a3 x to the power of 3, a3 is a constant, plus a2 x to the power of 2, a2 is a constant, plus a1 times x plus a0. And a's are constants here. So you have some number of operations that you need to do here. For example, you need to multiply x with itself 4 times here. And assume that all of these operations can take one cycle, multiplies as well as adds, and there is no communication cost, and each operation can be executed in a different processor. The question that I'll ask you, and there's no communication cost between different processors. The question I ask you, how fast is this with a single processor? Assume there's no pipelining or concurrent execution of instructions. Each operation takes one cycle in the single processor. Right? And that's the only thing that the single processor can do. It can do either one add or one multiply at a given time. That's the first question. And how fast is this with 3 processors? And 3 processors, each processor is the same as the single processor, but they can magically communicate these values to each other with 0 cycle latency, except the operations itself, each operation itself takes only 1 cycle. Okay? Maybe I'll leave you with this. Well, I guess I won't give you the solution. But after we take a 5-minute break, maybe you can tell me how fast is this with a single processor in terms of number of cycles? How fast is this with 3 processors in terms of number of cycles? And what's the speed up of 3 processors over the single processor? Hopefully, 3 processors will execute this much faster than a single processor would do. Okay, let's take a break for 5 minutes and let's get started. I hope you have the answers for me. So, what's the answer? How fast is this with a single processor? Any thoughts? I hear 8.
I said 18.
Say it again. 18?
19.
19 cycles.
But each multiply and each add is 1 cycle.
Okay. Really? That's a lot of cycles. That's a 19? Okay. Who else?
I got 8.
You got 8. Okay. 19 versus 8. That's a big discrepancy. Who
How
else?
many things can you multiply together?
I just said there's
Just
like-
one thing. One thing.
Well, yeah, it can't be 8 though.
This can't be 8.
X to the 4th is
There's
x
four
times
adds.
x times x times x. That's 4
But
right
it's
there.
4.
It is 5 multiplies 4 multiplies 3 2 1.
Yeah.
There you go. I hear something.
Oh,
Yeah, you could
yeah.
actually change the algorithm, change the way you compute it, instead of doing all of these literally, right? I believe I haven't gotten 19, but maybe you can get 19 by doing all of these one by one. But for example, you can reduce 19 because you've already computed x squared here. You can multiply that x squared by itself to get x to the 4.
Yeah.
Yeah, there you go.
If you write the assembly.
Okay, so 19 and 8. Anybody else? Let's see if which one? How fast is it with 3 processors, by the way? Have you done this? Okay. What about with 3? Okay. It's less than 6 actually. It's 5, but let's take a look. So this is one solution to the problem. This is a data flow graph drawn in some way, and it takes 11 operations. And assuming one processor can do 1 operation per cycle, it's 11 cycles, right? Basically, you compute x's here, x squared, x cubed, x to the 4th. And this is a1 x, this is a2 x squared, this is a3 x cubed, and this is a4 x to the 4. And then you add those together and eventually add a0. This is 11 cycles. So those of you who got an 8 may have gotten it wrong. And with 3 processors, this is one way you can do it, basically. You can do it in 5 cycles. This is x squared over here. I'm not going to go through this, but this is actually correct. Basically, with 3 processors, you can get 5 cycles. And I'll let you figure that out. With 2 processors, probably you can do it in 6 cycles, actually. That's probably the best with 2 processors. So your speed up with 3 processors is the time it takes to execute on a single processor divided by the time it takes to execute on 3 processors, 2.2, right? Which is not too bad, actually. You're using 3 processors to get 2.2x speed up. Is this good? Is everybody okay with this? Those of you who've computed 8, you're not going to challenge this? You'll challenge it?
Well, it's gonna. No, there's like latency everywhere.
No, latencies, ignore the latencies. Yeah, there's no communication latency. That's the beauty of this problem. But even with this is not a fair comparison. You should challenge me if you computed 8. Because the right answer is really 8 for a single processor. You can actually get T1 So this is actually the best you can do with 3 processors for this problem. But 11 cycles is not the best you can do with a single processor. So if you really would like to compute the correct speedup due to parallel processing, you should really have the best algorithm for computing on a single processor and the best algorithm for computing on the multiprocessor. And the best algorithm to compute this polynomial on single processor is not this. It was actually devised 200 years ago almost. You guys know the Horner's method or Horner's rule? Basically, you factor out the x's, and you can re-express this polynomial. It's a method of actually re-expressing polynomials or solving numerical equations. You can read this paper from 1819. It's almost 200 years. It's still beautiful. It's written nicely. Maybe a little bit mathematical, but that's the idea. Basically, express this polynomial this way by factoring out x's over here. And if you do this now, the number of operations is kind of obvious. You really have 8 operations over here. And the data flow graph is beautiful too. Yes?
Is that how Babbage built this calculating machine with that method?
With that method? I believe there was something that played into it, but I'm not sure. Maybe you can figure out and let me know. I'm curious now. Okay, so once you do this, the data flow graph looks like this. Basically, you really have 8 operations over here, right? And it takes 8 cycles to do this in a single processor. So the real speed up with 3 processors is 8 over 5 instead of 11 over 5. So the real speed up is actually much lower, 1.6. And this doesn't even include the communication latency, as you said. As you add communication latencies between processors, well, if you have communication latency, it makes no sense to partition this program in such a fine grain across different processors. But the speed up will go down as you add the communication latency. So this is the takeaway is you should do a fair comparison when you're actually designing parallel processors. If you want to compare power, performance, your algorithms should be really optimized for single processor as well as multiprocessors. Now, single processor algorithm is easier to optimize, obviously. It's difficult to optimize a parallel processor algorithm. So in this case, it's the best. What I showed you is best, but not in all cases the best may be obvious. Whereas in this case, single processor algorithm is best this way. So if you don't do fair comparisons, you could actually get into issues that look like this. Basically, you could get super linear speedup. By having n processors, you can get more than n speedup, which is usually, when you hear this, you should be very cautious. You should be very cautious to, and you can say, tell me more, basically. Why are you getting the super linear speedup? Well, what is super linear speedup? Basically, this is number of processors on the x-axis, and this is the speedup on the y-axis. Normally, in the best case, the speedup you should get should be linear. Everything else remaining the same, basically. You're not doing any unfair comparisons. But typically, your speedup is actually sublinear, as we've seen over here. Right? Speedup here is not 3. 3 means linear speedup, because you're multiplying the number of processors by 3. The speedup you're getting is 1.6. And typically, this is what happens. As you add more processors to solve a single problem, dividing the problem into tasks, your speedup tapers off, because your problem is not perfectly parallelizable. Right? So actually, speedup can be greater than p with pre-processing elements, even if you use the best algorithm for one processor as well as p processors, because you add more resources as you add processors. And these could be adding more cache, right? Or adding more memory, such that your working set fits in the cache or memory. Right? That's the other reason why speedup can be super linear. But that's, again, not a fair comparison in a sense, right? Because you're not only increasing the number of processors, you're increasing your memory as well. Right? For example, if your program requires a 4 megabyte cache, if it fits in the 4 megabyte cache, because its working set is 4 megabytes, if the single processor has a 1 megabyte cache, it'll get a lot of cache misses. Whereas if you have 4 processors, 4 of them together will have a total 4 megabyte cache, and the entire program will fit, the program's working set will fit into the cache of that multiprocessor, and you can get super linear speedup just because you're not missing in the cache again. Perhaps a more fair comparison is one processor with a 4 megabyte cache and 4 processors with 4 megabyte cache. Okay. So whenever you hear the superlinear speedup, always ask what's going on, right? It could be unfair comparison because the algorithms are not optimized for the number of processors, or it could be because of these memory or cache effects. Let's take a look at some metrics of multiprocessing. There are several traditional metrics: utilization, redundancy, and efficiency. I'm not going to spend a whole lot of time, but traditional metrics, these traditional metrics assume that all P processors are tied up for parallel computation. Basically, whenever you're doing this computation that I just shown, for example, all of the 3 processors are tied up until that entire computation finishes. Utilization is the measure of how much processing capability is actually used. Okay. We'll take a look at that. This is, actually, let me go into that. Utilization, how much processing capability you actually use. In the program that I've shown you, it takes 5 cycles to actually execute that program in 3 processors. Like basically, you have 3 processors, each of them you're tying up for 5 cycles. So you have 15 amounts of processing capability, or 15 operations you can do. But if you go back to this figure, we're not doing 15 operations. We're doing 1, 2, 3, 6, 8, 10 operations. Right? You're not using all of the processing capability that you're tying up. So utilization is really 10 over 15. Right? So you should be able to compute this relatively easily. And second is redundancy. Usually, when you add more processors, you need to do more extra work, right? And you can see this in the previous example. You have some number of operations in the parallel version, and some number of operations in the best single processor algorithm version. And usually, this is higher than this. R is greater than 1. Well, let's take a look at this example. In the best single processor version, you have 8 operations. In the best 3 processor version, we have 10 operations, right? Redundancy is 10 over 8. You're basically doing 25% more work, 1.25. Right? And in fact, this doesn't even include the communication operations that may be needed. Okay? And finally, the efficiency is how much resources do you use with parallel processors compared to how much resources you can actually get away with. This is the final metric of how efficient you are when you're doing multiprocessing. And you can see it this way. Basically, with a single processor, you're tying up 1 processor for T1 time units. And T1 should be determined with the best algorithm. In the previous example, you're tying 1 processor for 8 time units. So this part is 8. And in the multiprocessor case, you're tying up P processors for TP time units. Again, this would be the best algorithm. We were tying, remember, 3 processors for 5 time units. So this is 15. So your efficiency is really 8 over 15, which is almost 50%. So usually, when you have multiprocessing, you're increasing redundancy, and you're not utilizing your processors fully, because in this case, you see the load imbalance, right? You're tying up 5 processors, even though not all processors are executing 5 operations, right? This is load imbalance across processors. And as a result, you're reducing your efficiency compared to a single processor. But the hope is that you're executing faster. Right? Make sense? Okay. So let's take a look at some caveats of parallelism that we'll try to solve in some other lecture. This is a depiction of what I showed you earlier, actually. This is processors on the x-axis going from 1 to p. And this is speed up compared to a single processor. Execution time speed up compared to a single processor. It starts with 1, 1 here. Linear speed up if this curve is linear, right? Superlinear speed up, be careful. The reality looks like this. Why do you get this reality? Well, Amdahl's law, right? Amdahl's law, remember, this is time with P processors that could be divided into parallelizable portion versus the non-parallelizable portion. You have some time to execute the program on a single processor, let's call it T1. And let's say that non-parallelizable part, or parallelizable part is alpha fraction of the program. And non-parallelizable part is 1 minus alpha. When you add more processors, you can do nothing about this non-parallelizable part. Right? Non-parallelizable part is, regardless of how very many processors you add, you cannot reduce it. So this remains the same. But the parallelizable part, in the best possible case, gets divided by P. Well, there are some assumptions here, right? In the parallelizable part, everything can be executed in parallel by these different processors without any load imbalance. Right? So this parallelizable part can be parallelized perfect. Even if you assume that you get a curve like this, because alpha is not 0. Well, alpha is not 100%, right? If alpha was 100%, you would get linear speedup, right? Because in that case, Tp equals T1 divided by P. So let's take a look at, well, I guess let's take a look at Amdahl's law again. Amdahl's law says speedup is T1 divided by Tp, and if you actually reorganize this, this is what you get. Speedup is proportional to 1 divided by the parallelizable part divided by the number of processors plus non-parallelizable fraction. And as P approaches infinity, as you add more and more processors, your speedup is bound by this alpha. Your speedup is really 1 divided by 1 minus alpha. Let's say you have infinite number of processors and your parallelizable part is only 50%. The speedup, the maximum speedup you can get is 2. Terrible, right? You'd better increase this alpha. You have infinite processors and your parallelizable part is 99%, 0.99. The maximum speedup is 100. Again, it's terrible, right? Even if you have a parallelizable part that's 99%, which is very, very high, you get only 100x speedup with infinite number of processors. Well, that's why Amdahl wrote this paper that says, that was actually pretty pessimistic at the time. It says, basically, if you can read the title, it says validity of the single processor approach to achieving large-scale computing capabilities. He examined the programs of his time in 1967 and showed that this parallelizable part is not very large in many of those programs. It's actually around 60% or so in those programs. I believe he looked at database transactions, for example. And as a result, he developed this law, which later was dubbed law, actually, that says your speedup is limited by the non-parallelizable part, and maybe we should continue investing into the single processor approach because it's very valid to improve performance. Okay? So let's take a look let's do some plotting. Actually, I've already done this plotting for you, as you can see. But let's take a look at what Amdahl's law says. One conclusion is if you add more and more processors, you get less and less benefits over time. This is true if alpha has a value that's less than 1. This is not true only when alpha is strictly equal to 1. In that case, you get linear speedup. But if alpha is even slightly less than 1, you'll get a curve like this. You'll get diminishing returns. So the next processor you add, the marginal utility on performance of the next processor is smaller than the marginal utility of the performance of the previous processor you added. This is another way of looking at it. Here I plotted P, speed up over P. Here it's speed up over alpha for different P. And this curve shows that the benefit, the speed up is small until alpha is really close to 1. Whatever I said in words, this is in the curve. Okay. Regardless of however many processors you have, if alpha is not close enough to 1, you'll get a curve that looks like this. Well, you'll get lower speed up because this part of the curve is flat. So if you want to really get good efficiency from a multiprocessor, you'd better have a parallelizable part that's really close to 1. Okay? Well, we've already looked at this. This is another way of showing Amdahl's law. I think I renamed F. Renamed alpha to F here and P processors to N over here. Basically, maximum speed up is limited by the serial portion. Well, the serial portion over here. This is called the serial bottleneck, and we'll see examples of this. And we'll actually talk about heterogeneous multi-core processors later on that try to get the best of both worlds, that try to improve the performance of the serial part by having one core that's really optimized for serial processing, perhaps a very heavy out-of-order core that can improve performance of the serial part much better than a multi-core engine, and having many other parallel processors to improve the performance of the parallel parts. So heterogeneity would help here also, because these parts require different kind of processors. Right? The parallelizable part requires a processor that's perhaps wimpy, that's simple, although we'll see there are bottlenecks in the parallel portion as well. But the serial part definitely requires a processor that's complicated and, well, complicated may not be the right word, but that's definitely good at executing serial code, fast at executing serial code. So you need, even this equation tells you that you should be designing heterogeneous processors because these parts are really different from each other. Now, Amdahl was pretty pessimistic about multiprocessors. Today we see that actually there are a lot of applications where F is relatively high. This doesn't mean that F is infinite, right? If F was infinite, then you'd get actually perfect speed up, super linear, linear speed up. But there are many applications like graphics today where F is pretty high. That's one of the reasons why you have these massively multi-threaded and multi-core engines in graphics GPUs. But there's actually another caveat to Amdahl's law. What Amdahl's law doesn't cover is this. There's an assumption over here as well, right? Which is this parallel part is perfectly parallelizable. Which means that you can do this division, right? Once you have n processors, you're dividing the parallelizable part by n. And the performance is improving nicely and perfectly in that part. Unfortunately, that's not true. The world is not as rosy again in this case, because the parallel portion is usually not perfectly parallel. Why? Any thoughts? Yes.
Synchronization costs.
Mm-hmm.
Waiting for the other threads to complete, for example.
Exactly. When the threads need to communicate with each other, they need to synchronize, right? For example, when they're accessing shared data, when one thread is updating shared data, the other cannot access it. As a result, you need to synchronize. So locks is an example. Locks are an example of this. The other example is barriers, right? Remember the example that I showed you on parallelization? You actually have multiple threads that are computing 1/4 of the book to compute the histogram of the letters in that portion that are assigned to them. Eventually, you need to compute the entire histogram. And to be able to compute the entire histogram, you need to wait for all of the threads to finish their computation. And threads may finish their computation at different times, right? So you need to synchronize between threads so that you can move to the next step where you actually gather together those histograms. So you get synchronization overhead. And that serializes some threads. Now you cannot do this perfect division, right? What else? Actually, two more. One of them you've seen. Actually, both of them you've seen, but one of them you've seen really, really heavily in memory interference lectures. Resource contention, right? If the threads are sharing some physical resources and the resources are not perfectly parallel, one thread may need to wait for the other thread to access the resource. As a result, you're basically serializing the threads, right? That's a physical reason why parallel portion is not perfectly parallel. We'll get to that, but the third one is load imbalance. Load imbalance happens because you may have imperfect parallelization, right? And this is, again, I'll use the same example that I've shown you earlier. Let's say you have this book, you're dividing the histogram computation into 4 threads, and you assign 1/4 of the book to different threads. And it turns out that the first 1/4 of the book consists of a lot of pictures, and the thread doesn't have a lot of work, and that thread doesn't have a lot of work. As a result, that thread has much less load to compute the histogram, right? So it waits for all of those other threads to finish until it can move on to the next step of the program. This is an example of imperfect parallelization. In this case, the data happens to be such that you get load imbalance between the threads. Make sense? But the takeaway is that you're not perfectly dividing your program into n pieces, which means that this doesn't hold. Right? This holds only if you're perfectly dividing the amount of work that's parallelizable into n pieces. And we already talked about the resource sharing overhead. If you have contention among n processors, you can actually serialize the processors. So this is actually a tough thing to do also. It's not only tough to improve the serial part, the parallel part is not perfectly parallelizable. And we'll actually take a look at this later on when we talk about heterogeneous multicore. Perhaps you can have, whenever you have not perfectly parallel parts in the parallel portion, you can use a heavy-duty single-threaded processor to actually get rid of those parts or get out of those parts quickly. For example, if you have a critical section that takes long to execute and that's causing a lot of serialization, perhaps you execute that critical section on a heavy-duty single processor such that the parallel portion performance improves, such that you reduce the serialization. And we'll talk about that. This is called accelerated critical sections. Instead of executing the critical section on a wimpy core, execute it on a powerful core. You could do it for load imbalance also. For example, you could detect threads that have much more work and execute them on much more powerful processors. Right? Instead of treating everything equally and executing everything on an equally wimpy processor. Right? Resource sharing is a little bit tougher, actually. If you just don't have resources, you can do intelligent prioritization. For example, you could prioritize those threads that are on the critical path of execution in your resources. In the memory scheduler, somehow, we've actually briefly talked about this when we talked about memory scheduling in the last memory interference lecture. Remember, I had a slide on memory scheduling for parallel applications. Right? If you can figure out which thread is the critical thread, which thread is the bottleneck for your performance, you can somehow integrate this to your cache, to the cache, and to the memory controller that's shared across different threads. And the cache and the memory controller can prioritize that thread, such that you can reduce this resource sharing overhead, such that you can alleviate the fact that the parallel portion is not perfectly parallel a little bit. So there are potential solutions to this, but Amdahl's law doesn't even think about this parallel portion not being perfectly parallel. Okay, this is an illustration of the sequential bottleneck with numbers. I've already shown you this actually. This is parallel fraction over here, speed up over here, and the number of cores. The curve is plotted for a different number of cores. If you look at this, it's the same thing. If your f is small, your performance improvement is not high, even if you have 1,000 processors. And performance improvement starts being very high only for f's, the parallelizable fractions that are, in this case, greater than 96% yield. This is the reason why, remember the Cray 1 machine design that we've discussed? It had it had the fastest scalar unit of its time. Well, that's exactly the reason. So that they can improve the performance of the serial part, not only the parallel part. So why do you get the sequential bottleneck? There are many reasons for this, but all parallel machines have sequential bottleneck. If you have some part of your program that's sequential, you'll have that bottleneck. And if someone tells you that they don't have the sequential bottleneck, you can ask them, tell me more. Even the biggest distributed systems have sequential bottleneck because there's some amount of work that's just not parallelizable. For example, you can have non-parallelizable operations on data, right? You can have non-parallelizable loops. Right? In that case, you need to do something sequentially. Maybe not the entire loop body, but something sequentially. Or you could have a single thread that prepares data and spawns parallel tasks. Right? Even if it takes a very little fraction of the time of the entire execution, that's still sequential, right? And that still makes you subject to Amdahl's law, right? Or at least the consequences of Amdahl's law, which is the diminishing returns on performance. Or in the example that we've discussed, you could have a single thread that's gathering histograms, right? So let's say you've divided your book into 4. Each of the threads computed the histograms. Then all of them waited for this barrier. And at the end, what do? One thread gathers the histograms together. Or you could have a trio of threads gathering the histograms and do the same thing again. But still, the part will not be perfectly parallel. You'll have a sequential part. There are many other reasons. This is one other example. This is here, for example, spawning the threads, initialization functions. This is really the sequential part. I should have a better picture for this when we talk about heterogeneous multicore. And this is the locking and unlocking is an example of bottlenecks in the parallel portion. So let me cover bottlenecks in the parallel portion, and then we'll conclude hopefully soon. So let's go into these a little bit more detail. Synchronization. Remember, these are 3 things. These are 3 buzzwords that you should really know. Synchronization, load imbalance, and resource contention. Right? Those were 3 bottlenecks. Why do you have synchronization? Because operations manipulating shared data cannot be parallelized. These are operations like locks, mutual exclusion, barrier synchronization. This is another form of communication. Because threads need to communicate with each other, this happens, right? Well, in this case, they communicate through the shared memory. Right? They need to synchronize through the shared memory. As a result, you have these synchronization operations. Tasks may need values from each other. If you have this is true for tightly coupled multiprocessors, right? But synchronization is an issue with loosely coupled multiprocessors also. We haven't talked about them as much, but whenever you send or receive messages, if you're waiting for those messages to do some work, then you're really serializing the program, right? Serializing the parallel part on a loosely coupled multiprocessor. So all of these affect any kind of parallel processor. This causes thread serialization when shared data is contended, and we'll take a look at that later on. Load imbalance, we've already talked about this. Parallel tasks may have different lengths. This could be due to many different reasons, but one is because the programmer didn't partition the program perfectly, parallel part perfectly, or it could be due to microarchitectural effects. For example, you may have some tasks that keep missing in the cache, but some others have good locality. Right? The programmer partitioned it nicely, but somehow this task becomes unlucky and misses in the cache. Or this task accesses some part of memory that's contended by some other I/O device, let's say. As a result, you may get load imbalance microarchitecturally as well. And this reduces speed up in the parallel portion. And finally, resource contention. We've already talked about this. Parallel tasks can share hardware resources, delaying each other. Now you can eliminate this. This is the part that you can potentially eliminate. You can replicate all the resources, right? But this is expensive. Actually, that's why people do not do it. And replicating all the resources may not be a good idea also. In this case, you're actually kind of replicating the resources, but you still have resource contention because the processors can access different parts. Because replicating resources can reduce the speed of communication, right? For example, if you replicate the caches, it may be better to have a shared cache than replicating the L1 private caches, right? Because shared cache enables faster communication. One of the biggest downsides of resource contention is this can lead to additional latency that's not present when each task runs alone. And we've seen this in memory controllers, right? You can have two tasks that have good robuffer locality, but when they run together, you get robuffer conflicts. Right? And those robuffer conflicts lead to cycles where you cannot utilize the memory system because you're pre-charging the bank. Okay. So a lot of the difficulty in parallel programming, and as a result, a lot of the research that's done in parallel processors, and especially multi-core processors today, are related to all of these things that we've talked about, plus one more thing, which is getting the parallel programs to work correctly. So there's little difficulty. Parallel processing is great if parallelism is natural. If you have embarrassing parallel applications, for example, multimedia, physical simulation, graphics, usually these scale very nicely as you add more processors. But even they have the sequential parts, sequential bottleneck. Large web servers, databases, for example, these are another example. But databases may have, if you're accessing shared data, if you're updating shared data frequently, you can get difficulty in programming them. Usually the difficulty in parallel programming is getting the parallel programs to work correctly, which we will cover briefly in the next lecture. What can the hardware provide such that parallel programming is easier? You can actually run, how many of you have programmed in parallel? Is it easier than single-threaded programming? No, right? You get into all of these bugs, right? That is very hard to debug. But this is one of the big issues with parallel processing. And the second is, assuming that you've gotten them working correctly, that doesn't mean that you've gotten them working at high performance. Right? How do you optimize performance in the presence of bottlenecks? In fact, it's really easy to get parallel programs to work correctly, right? You can have, I don't know, you can identify the function that you're going to parallelize and you can lock it and unlock it. Now you have a perfectly parallel program, as long as you have a very coarse-grained lock. But now you're back to square one because you're actually serially executing all the parallel parts. And you have the locking overhead, which is probably reducing your performance. So maybe this is trivial if performance is not a constraint. But performance is always a constraint. So how do you optimize performance in the presence of these bottlenecks? As a result, much of the parallel computer architecture research and development is about designing machines that can overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency, and making the programmer's job easier in writing correct and high-performance parallel programs. And these are actually tightly coupled in some sense. Because if you optimize the performance in the presence of those bottlenecks, you're kind of alleviating this first part, the burden of this first part a little bit from the programmer. Because you're telling the programmer that, oh, even if you write a little bit crappy parallel programs in terms of performance, I'm going to execute them faster. And by the way, you can write those crappy parallel programs and hopefully get them correct instead of trying to optimize those programs such that eventually you'll get a fast program as well as a correct program. So the problem is interesting because if you have support in hardware that could get rid of a lot of these bottlenecks, the programmer can program more liberally, or they can slack off, if you will, and not optimize their programs as much. They can have, for example, long critical sections. But if the hardware is accelerating those critical sections, hopefully they will get the program correct, which is the first step in executing a program. And the hardware can speed it up transparently, or mostly transparently. That way you get both correct programs and fast programs. So we'll take a look at that approach when we talk about heterogeneous multi-core also. Okay. Any questions? And if you want to go deeper into a lot of these issues, we'll talk about them in 742. That's what 742 is about as well. Okay, I guess if no questions exist, let's stop here, and I'll see you Wednesday.